and you look at the nth power map, that's surjective with kernel mu1. Okay? So if you want to look at H1 of the Galois group of F bar over F with coefficients in un, Hilbert 90 says H1 of this Galois group with coefficients in F bar star is 0. So the boundary map gives us an isomorphism between this and F star mod F star. So that's the basis of Kummer theory. And what McCallum and Sharifi do is, instead of looking at the Galois group, the entire Galois group of the algebraic closure over F, they look at the Galois group of the maximal extension of F that's unramified outside S. And they study the pairing between H1 of that with coefficients in un, that shouldn't be there, into un twisted twice. So there's an extra in there.
So you're just using the tensor product.
Just using, yeah, this is just the cup product pair. So it's a cup product pair. So the basis for all of these things is a cup product. Now, the other thing that they do is to say, okay, this pairing naturally lands in this H2. Again, that shouldn't be there. But you can restrict to the decomposition groups it places in S. And there's a standard exact sequence in Galois cohomology that says that the kernel of the restriction map is this quotient. Okay? So what they've done is, if you take classes in this H1 and this H1 that come from these elements, all of their local Hilbert symbols are trivial. So you know then that the value of the pairing lands in this global object. So the interest in the McCallum-Sharifi pairing was that it's a way of pairing rather explicit concrete elements of F to produce interesting global objects.
And
in
you're
this
just
kind of
using the
question.
box type.
Pardon me?
You're using just the box type homomorphism in the exact sequence to take it.
Right. No, yeah, exactly. That's where that sequence comes from. Okay, so why did they do, what's some consequences of this? When you take n to be a prime, they analyze how you can use this pairing to understand generators and relations for this algorithm. And there's a conjecture that Ralph Greenberg made that says that if you take any number field F, talk about Greenberg's conjecture since it's a really important thing. F is any number field. You look at the composite of all the ZP to the ZP extensions, so that you take the composite of all the ZP extensions. The ZP is periodic numbers. Now, then you could look at the maximal abelian unramified extension of L. And this Galois group here is a module for the pro-group ring of this Galois group. Okay, so this pro-group ring is a nice thing. It's isomorphic to a formal power series algebra in D variables. It's a nice regular ring. And what Greenberg's conjecture says is that not only is this a torsion module, it's supposed to have trivial localization in every codimension 1 prime. It's pseudo-null. So that's sort of the first step in trying to understand Iwasawa theory beyond localizations at codimensional primes. You'd like to say that in this situation, even the localization codimension 2 primes, they're all 0. In general, if you replace this by some other group, it can still happen that this is pseudo-null, that localization to codimension 1 primes are all 0, but some codimension 2 primes, the localization is not. You'd like to know what's the length. And that's what really motivated our working on Chern-Simons invariant. We were trying to understand how do you develop Iwasawa theory in higher codimension. We're going to need new numerical invariants beyond p-adic L series to do that. The interest is whether these kinds of pairings will help. So in any case, McCallum-Sharifi pairing, there's been some basic work on this. It was the motivation also for Sharifi's conjectures, as I mentioned. And the question is, okay, so what kind of pairing is related to the Mignon's invariant? And there is one, and it's different. So here's the way it works. You take a cyclic, again, we're using the same objects. A is that the nth root generates a cyclic Kummer extension of some degree dividing them, and we're taking units on the other side. And then you do the same things that I was talking about before. Any unit is a local unit everywhere, therefore it's a local norm everywhere, so it's a norm. And then you can find, okay, so by Kummer theory, you know there's a generator, so that sigma sends a 1/n to some nth root of unity. And you can again use Hilbert 90 to produce an element mu, so that sigma mu over u is this x to the m over d. And you go through the basic computations that we were doing to compute Mignon's invariant, and you come up with an ideal whose nth power is a particular norm, and you write down this pairing. And this pairing actually is independent of everything. It's independent of the choice of zeta n. And it, you can write down the Chern-Simons invariant. It's a special value of the pairing where you take an nth root of unity as the unit value. So the question was, what can you say about the relation between, what's fascinating about this to me was that you have the Sharifi pairing, you have the same groups, but values in a somewhat different target than this one for Mignon's. So the question is, what's going on? They're really definitely different. You can find examples where Kim's invariant is not trivial, the value of the McCallum-Sharifi pairing is trivial, and it's not because the target groups somehow degenerate. I mean, the class group always maps to the S-class group. In fact, one of Mignon's first example in their paper with the 6 alphas. So now I'm just going to finish with a little comment that what we're working on tonight. So the question was, how do you look at Kim's invariant and the McCallum-Sharifi pairing in the same frame? And the idea is this, that as I mentioned earlier, instead of talking about cohomology classes in H3 with coefficients at Zn, you look at X classes. So I was talking about the value of considering X. Remember that if you take Hi of X Z mod n, we're just talking about X I with X of the constitute Z coefficient. So all we're doing is saying replace the first argument by Z mod n, and so you're going to end up with short exact sequences of this type. I sort of indicated why earlier. Now, the pairing that gives rise to Mignon's invariant is really coming from this, when G was a cyclic group of order n, because then if G were a cyclic group of order n, and I think about group cohomology, a generator for H3 you can form by cupping a generator for H1 and H2. And somehow it's this pairing that is the cup product pairing in a tall cohomology is what's behind the computation of Mignon's invariant. But now there's a cup product pairing in X groups. And what's interesting about this is that you also have a pairing of H1 and H1 to H2. Okay? That's related to McCallum-Sharifi, because if you remember what I had with McCallum and Sharifi, it was coming from, if I think of Z mod n as mu n, you had H1 of mu n potentially cupping with H1 of mu n going to H2 of mu n just to twice. So you have a pairing of this with this, with values here. So what we're working on showing is the following. We can look at the pairing that gives rise to the Mignon's invariant by simply taking elements here, you lift them back to here, you cut them here, and you get Mignon's. And then, but for McCallum-Tarifi, what you'd like to say is if you take an element here and an element here, and you're trying to put the cup here, well, you just take any lift, cup it with the image, you get a class in here that's the image of the McCallum-Tarifi. And, okay, so we haven't finished writing out the details of that. We do know, I believe, that if you take something here and here and push them forward, they cut to 0. So, because of that, there's really, it's a preposterous idea to say that there's, well, it seems unlikely, but you never know, that there's 2 different ways to pair these groups together. Because this does pair with the image here to 0, one way to do it would be to say, take any lift, push them forward, and pair it here. You're going to definitely get something 0 here, so you get a pairing there. But the logical thing would be to say it comes from pairing this to this to there. But we haven't written out those details. Anyway, I think it would be good to pursue the unification of these pairs in Galois homology that are related to Mignon's work and the McCallum-Tarifi pairing, and via Tarifi's conjectures related to modular forms as well. So, that's just about all I wanted to say.
Questions? Interesting mistakes.
I have a provocative question.
Sure.
So, when I think about Chern assignments, I think about transgression on Chern classes. You take a Chern class for something that's like a one dimension greater than the manifold you're working on, and you transgress, and then you get a 2n minus 1 form, and that's what the Chern assignment invariant is. But it seems like what you guys are saying is any third cohomology class of the group, you pull that back, and that's the Chern. Is it true that in fact that there's some universal statement that you're always pulling back the result of transgressing a Chern class?
I remember talking to Peter Simons about this. In other words, what we took advantage of here was if you have a cyclic group order n, you can construct a generator for the cyclic group H3 by cupping something in H1 and H3. And as Mignon said, you can start with something in H1, take its Blackstein, and take the cup. But in general, I think for an arbitrary finite group, there's elements in H3 of the finite group with coefficients in UN that don't come from cupping. I mean, in particular, if the group were perfect, then you're not going to have anything in H1. And Simmons has interesting formulas for how to construct elements in H3, but you're going to have to do something else. In your examples, were you always able, in the examples that you dealt with, you had an S4, Klein 4, C02. Were you always able to realize the class in H3 that you wanted as a cup? Something in H1 and H3?
Yes, we always work with like
in the
cup products of H1 and H2.
Yeah. Those are more accessible, but absolutely, you're going to have to do something more.
In your non-trivial Chern-Simons invariant example, you said there are infinitely many examples. And can you explicitly write down the number field F?
Yes.
Sure.
Yeah, you can. You can write that down. But they tend to be kind of big.
How big?
Well, let me see if I can remember. I mean, I remember what the problem was. It was sort of. I don't want to go on about this too long. So. The problem was really, it's easy to construct infinitely many Fs that have cyclic unramified extensions a degree and so on. That's easy. The hard part is to construct Fs that have such extensions at the same time as having single primes, which are then undecomposed in some cyclic extension of degree. And what we did was, I don't know if I can remember it now. We had to use an argument that involved first taking a particular first approximation to the field we want. And then we had to make an extension of degree n squared, which was ramified only over one prime. But we did it by adjoining an element, an n squared root of some element, which generated, which had the property that it was an n squared power at every prime over n in F. So we needed a lot of control on the other primes over n in this field, in this extension. And then we had to do a further twist. So we didn't actually try to, but I mean, yeah, it takes a bit of work. I mean, in other words, it's not the most efficient way to do it. You have to first pick a very good extension in which there's one prime over n that's totally ramified, and all the other primes are split. Then you work with that, you torture that. You basically take that extension and then you make some degree n cubed extension of this one. This does degree n cubed. This has degree n, and we realized the L inside there. That was the kind of thing we ended up having to do. So I don't think I can, but we can talk about it after.
More questions? Thanks again.